Hello everybody, how's it going today? My name is Connor and welcome back to another video. Today we're going to be talking about the parser that I've created, how I've kind of created a parser for my scripting language for Paper, my audio runtime processor. And then I kind of decided to scrap it and I decided to make a better one. Um, so we're going to be talking about both versions today. But first things first, you may be noticing that I'm sounding a little different. It's because I'm using the built-in mic on my laptop instead of my USB mic that I think was causing some issues with the audio crackling. I've also completely reinstalled the operating system using a different Linux distribution. As you can see, I have a little Pop! OS prompt down here instead of the Fedora prompt. So hopefully the audio issues should be fixed. Hopefully I can understand me clearly enough in this video because it's gonna be a long one. So um, like I said, I've kind of created two different versions of the parser and two different versions of the syntax actually for the scripting language that I use for Paper. So uh, first things first, I want to kind of compare and contrast the two versions. So let's go into my test scripts here. That's the second version. Let's go into the first version. Okay, so this is a good example of like next a simple example. So let's talk about what stayed the same. So if we kind of compare these two versions of the syntax, um, you can see that each one allows us to define a number of different graphs, right? So you have the main graph down here, main graph over here, and then you have other graphs like this test one over here, and then this manual sign oscillator over here, right? For the second version. So, um, and yeah, so each graph has a number of different input and output parameters that you can specify, and it also contains a set of statements denoted by this tilde and open brace here that allow you to connect the inputs and outputs together, right, in different ways. So, and the result is you get these graphs that are each a an individual audio processor that can takes control and audio inputs and outputs. Um, so, and then within this connection logic, you can actually also define other graphs. Like here is an example in the first version of syntax where we create an instance of this test graph up here. And then over here in the new version, you can see we've creating an instance of the manual sign oscillator over here, right? But you see the syntax is quite different. So I'm going to get into that in a bit. And also, what stayed the same between these versions is that they each distinguish between audio rate and control rate signals, because those are the two main types of graphs that are happening in the application in the actual runtime. So you can see the audio rate signals are denoted by, should be denoted by a little at sign before the identifier for the signal name. And then the control rate signals are denoted by a little hash symbol, little number sign, pound sign symbol. So that stayed the same between these two versions. You can see that we have the pound sign for the control rate inputs here, and then we have the at sign for the audio rate output. So I want to talk about the parser for the first version now. And in addition to the parser, I want to talk about the grammar a little bit and what I didn't like about it. So let's go over here to the parser module for the first version, right? I'm gonna get rid of that, get rid of this. So I'm just gonna do a quick scroll through here. And as you can see, it's pretty messy. This parser is about 1,000, about 900 lines of code. And so, but it's just a complete mess. I'm using the nom crate, crate called nom, in order to parse the text directly from the source file. And I just kind of create the graph as I go with that. And that is just a really terrible way to do things. Like, I'll talk about in when I get to the new version that it just, new version has an actual tokenizer and actual tokens that I can match over, and it's just a much more cleaner much cleaner setup. So as you can see, I have like this, you know, because I'm matching over the text directly, I have this ignore garbage parser combinator that basically just trims out any white space or comments, you know, in between any, what would normally be a token, right? So that just is just everywhere in this parser. Because if I don't explicitly do that every single time, then it's gonna match on a comment and get confused, right? Or get match on white space and get confused. So that was just a real pain in the butt. And in addition to that, the parser, when I actually created the nodes in the graph, it actually used their names, their string names, in order to refer to them. Yeah, here we go. Node ID by name. This is like, let's count how many times this is in this file. Yeah, 22 times, right? So I'm just referring to them by their names and not by their actual like input or output indices or what have you. So excuse me. Drinking some water. So that was just not great. Because some nodes they could have, some nodes that automatically generated names, and sometimes those names could be the same as other nodes. So that could lead to collisions in the internal hash table, and it was just a big mess. Um, so yeah, and also in terms of the actual syntax for the parser, sorry, the actual syntax for the language, for the first version of the language, as you can see, each and every identifier in each every node and signal has to have an explicit rate associated with it. So as you can see, when I create a sorry, as you can see, when I define this test graph, see I have separate audio inputs, audio outputs, control inputs, control outputs, right? So there's no auto detection of anything going on here. There's no inference. And in addition to that, if you mixed different signal types in the same like expression, like if I were to do like mix a audio rate signal with a control rate signal in the same right-hand side of an expression, then that would actually cause a parser error. And that was not allowed. So, and in addition to that, every single time I wanted to use an external node or a built-in node or a graph that was defined inside of the script itself, I had to explicitly create it with this create keyword, and give it a name. So, and then I had to connect every individual input and output manually that I wanted to use. So, and you see it was just a complete pain, you know. Um, so, and, and if that didn't make things worse, then if I were to say have a node that had that had more than one output, or a graph that had more than one output, then there was no way to unpack that. It was basically like I couldn't do like A, B, um, test, right? Or something like that. I hope or more like that. You get what I mean, right? Like, if say test had two outputs here, I couldn't just unpack them like you can like a Rust tuple or something, or like a Python tuple, So, that basically made those test nodes way less usable. So, but that's more of a minor thing. That's not really useful to me right now because all the nodes that I've created only have one output anyway, but could be useful in the future. And that's something that the new parser does have support for anyway, so it just makes this one inferior. um, so let's talk about what was improved with the new version of the parser. So again, I'm going to open up the syntax 2 here, and I'm actually going to open up the parser2 module file. So this one actually has more lines of code. I'm pretty sure it has, around 1100, almost 1200 lines of code in this one parser file. But the thing is, this code is way more organized, way cleaner. Things are much more modularized, and a big part of that is because I actually have a token enum. Right? I know, right? It's freaking unbelievable. But as you see, I'm still using nom for the matching, but this time around, I have um, the tokenizer, which is just this parse function on the token struct, token enum, that will basically match any of these tags, and then it will, or any of these custom parsers like the identifier, or a number with a float or comment, or white space, and it'll just turn them all into these, versions of this tokens enum, right? So, um, sorry. And then I have this tokens struct, which is just a wrapper over a slice of tokens. And then what I've actually done is I've implemented all the necessary traits for nom to be able to actually match over this tokens this tokens struct, right? This custom list of tokens. It's just a quick little wrapper, in order to do that. But actually, I know I'm using that. Get rid of that. So, and see here, I have some of the original stuff in order to recognize the comments, the white space, the identifiers. But either way, and then don't need that anymore either. And then I was able to use this macro that I kind of, didn't steal, but it was inspired by this certain macro in the Monkey Rust crate, which uses a similar process in order to match over the tokens using nom. And it's just like a custom tag for tokens rather than for strings, because you can't use custom tags with the tag function in nom for whatever reason. You don't use it with strings. So this just implements a bunch of matching functions in order to match over certain tags or tokens, certain specific tokens, I should say. And I have I have parsers to turn the tokens. Yeah, so I have parsers to turn the tokens. Sorry, I'm freaking fried. Into the actual types that they're supposed to represent. So I have all of these custom structures that are actually part of the abstract syntax tree, the AST, abstract syntax tree, or AST, sorry, of my project, or of the scripting language. So it's a lot to go over. I don't need to go over every implementation detail. If you are interested, you can look at the source code for my project. It's on GitHub. I'll link in the description. It's under the parser2 module. That's the second version of this parser. So, yeah, and then I have some actual things to solve or I should say resolve, but I just chose solve instead, I guess. But to resolve these expressions and turn them into actual AST structures that, going from the parsed expressions, which just contain the raw tokens, right? Or yeah, something like that. They contain the tokens and the AST structures. Sorry, I should say. The parsed the parse, any structure starting with parse is like part of the AST, and anything starting with solved is information that's used to actually construct the graph. So anyway, point is, um, yeah, so the new version is way cleaner. um, it's way easier to work with. It's way more flexible. It allows me to do things like matching over the tokens themselves and actually filtering out the white space. In fact, yeah, here we go. So I can actually, that's ignoring comments right now. Okay, well, either way, I'll fix that later. Dang it. Okay. So, here. There we go. So, either way, that's kind of scuffed, but I do things like filter the tokens and filter out the white space and filter out the uh, comments preemptively before they even go into the actual token parsing stuff. So anyway, um, so besides that, let's talk about the syntax that's improved with the new version. Um, First things first is that um, the signal rates can be mostly automatically inferred now. So it actually allows us to create graphs that are completely generic over their signal type. So what that means is, as you can see in this new syntax, this is actually what the inputs are, and this is what the outputs are after this little arrow. Just so you know. Otherwise, it's mostly the same syntax. And also the assignments are equal signs now and not well, let me wait. They're equal signs now instead of left arrows, like they were in here. You see, just because equal signs are easier to type. So as you can see, I can have identifiers for my inputs and outputs that don't even have a explicit signal rate with the @ sign or the pound sign before them, right? So, and as you can see, there's actually nothing with any kind of @ sign or pound sign before it in this entire graph definition. So what that means is that I can create either a um, completely audio rate version of this, or I can create a completely control rate version of this. And it allows me to reuse the same code for different applications, right? So that's a really big plus of this new implementation, is that it's kind of smart, and it'll kind of try, it will automatically detect what, rates, what signal rate each input and output and graph should be. So, um, and obviously you can still make them explicit if necessary. Like here we have for the main graph, we have all of its inputs are explicitly control rate, right? And the reason for that is because when you create a uh, a built-in or an actual graph instance, you can specify, like I said, you can specify its rate or not at all, and have that automatically detected. But say you want to put a control input into an audio rate node or graph, then if you don't if you don't manually explicitly specify that these are control rate signals, then it's going to assume that these are going to be audio rate signals, and you might not want that, right? So either way, and as you can see, there's now the ability to actually make it a bit more like an imperative language rather than declarative language, um, where you can have the node instantiations and the graph instantiations be more inline, right? So like versus in the first version, you had to manually create the nodes and give them names and assign their all inputs and outputs manually. You can just use it like a regular like function call, like in another language, right? In the second version. So this, and it's important to realize that these two sign-off manuals instantiations are going to create different versions of this sign-off manual graph, right? So it's two different instances. It's not just calling a function like it is, um, like it kind of looks like it is. It's actually more so like creating an object in like an object-oriented programming language. So, um, yeah, and then you can specify the arguments in order, the inputs in order, and it'll just automatically map those to wherever they need to be. You don't need to specify the names of inputs or anything. Although that is a feature I would like to add in the future. So more like a keyword argument rather than a positional argument. So um, so let's talk about what I would like to have for the new version in the future. So the old version of the syntax would actually let you have default values for control inputs, and actually only control inputs. But as you can see here, this input 0 has default value of 0, this input 1 has a default value of 0.5. And this control input 0 has a default value of 50, and this one CI1 has default value of 150. By the way, the parentheses and the colon and then there are like they're just defining the range for the UI element in the main graph. So this is what you actually see on the application when I actually run it. You'll see the sliders, and they have all the inputs that are defined with slider values. So this is what the parentheses mean. But anyway, yeah, so you can define default values for these. And you actually do it for any graph, not just the main graph. Whereas in the new version, you can only do that for the main graph. And I think the part of the reason for that I haven't implemented something like that yet is because of the whole keyword argument thing. Because they're positional, you would need to specify them as keyword arguments rather than actual built-in arguments, and it'd just be a mess. So, but that's something I would like to do in the future. Also, what I would like to do in the future is having what I would like to call a do statement, and var statements. So what that would look like is something like do, and then you could have like a var f equals 4.0, right? And then what this would do is this will allow you to reset and reuse these variable values, and also possibly even having them like static variables just as part of the graph itself, is so you have some kind of mutable state, right? And what the do statement would do would let you actually do things in order, in a certain order. So that's another thing that I kind of forgot to mention, honestly, but every single one of these connections happens in parallel. They're all just set up before the graph even runs, and they're actually, it's not like, oh, first I'm letting tau equals, the value of 2 pi, and then I'm assigning s to the sign of, whatever, and then I'm assigning the output to whatever. No, this is, I'm creating a constant called tau, and then I'm going to plug that constant into this sign function, while the output of the sign function is going into the output. And you get what I mean, right? So they're all happening in parallel. It's not a sequence of connections. It's a list of connections. I hope that makes sense. So what the do block would do in the future is allow me to have sequences of connections, or sequences of assignments or calculations that all happen, in a certain specified imperative order. So, and then the var would let me kind of have reusable connections that could be, or reusable values that could be set and reset to different values. So anyway, that's about it for this video, honestly. It's going on time. Yeah, so that's about it for this video. I wanted to mention that if you haven't heard, I am now a YouTube partner, thanks to your outrageous support. for my channel, which means you can now become a member of my channel. I have 2 tiers of that. One called Bit, which is I think $3 a month. One called Byte, which is $7 a month. They each have their own perks, and of course the Byte perks involve all of the perks of the Bit tier. So um, anyway, if you like this video, please leave a like. If you want to leave a comment on this video, leave a comment. If you want to see more of my videos like this, where I just kind of ramble about my projects, then you can subscribe. If you want to support me, like I said, you can become a YouTube member or give super thanks at the bottom of the video page or whatever. Other than that, thank you all very much for watching. I'll see you in the next one. Peace out.